Hello and welcome. I'm so glad you're here. Before we begin, I'd love it if you could share in the comments where you're listening from and what time it is for you right now. It's always a joy to see people tuning in from different corners of the world and at different moments in their day or night. I also want to take a gentle moment to thank those of you who have already subscribed to this channel and who keep pressing that little like button on the videos that you find most valuable. It truly helps me know what resonates with you, and it helps others find these calming spaces too. And if you ever have ideas or topics you'd like me to explore in future videos, please feel free to suggest them in the comments. Your thoughts and inspirations are always welcome here. So, with that said, let's begin. Close your eyes and let the quiet of the night settle around you. Feel the gentle rhythm of your breath, the way the air moves in slow, silent waves. Now imagine a tiny particle, no larger than a grain of sand, existing in a state that defies our everyday understanding. This particle, like an electron or a photon, does not exist in one place or one state at a time. Instead, it exists in a multitude of possibilities, each one as real as the next, all at once. This is the wonder of quantum superposition, a gentle dance of potential that reveals how the universe operates at its most fundamental level. In the world of the very small, where the rules of classical physics no longer apply, particles do not have fixed positions. They are described by wave functions that spread out like ripples on a pond. When we say a particle is in a superposition of states, we mean it is simultaneously in many places and many energy levels. It is as if the particle is a wave of potential, a gentle pulse of possibility that ripples through the fabric of space. This wave function does not represent uncertainty. It is a real physical description of where the particle might be found. Before we measure it, the particle exists in all possible states at once, like a single drop of water falling in a gentle rain that touches every leaf in the garden. Erwin Schrödinger, the brilliant Austrian physicist who first formalized this idea in his wave equation, understood its profound implications. He wrote in a letter to a friend, "The particle does not exist in a single state, but in a superposition of states. This is not a trick of the mind, it is a fundamental reality." Schrödinger's work revealed that particles behave like waves until observed, and this behavior is not an illusion, but a deep truth about the universe. Think of a child's breath on a cool night, soft, invisible, and flowing in all directions at once. That's the essence of superposition, a single particle holding the potential to be in many places, many states, all at the same time. To understand this better, consider the double-slit experiment. Imagine a beam of electrons passing through two narrow slits in a barrier. On the other side, they create an interference pattern on a screen, as if they are acting like waves. But if you try to observe which slit each electron goes through, the pattern disappears and you get two bands of electrons. The act of observation forces the electron to choose a single path. This happens because the wave function collapses when measured. Before measurement, the electron exists in a superposition of both paths simultaneously. It is as if the particle is waiting to be seen, holding the entire garden in its breath. Schrödinger himself devised a thought experiment to illustrate this strangeness. Picture a box containing a cat, a vial of poison, and a device that releases the poison if a radioactive atom decays. The atom has a 50% chance of decaying within a certain time. According to quantum mechanics, until we open the box, the atom is in a superposition of decayed and not decayed. Therefore, the cat is both alive and dead. This thought experiment was meant to show how quantum mechanics applies to macroscopic objects, but it has become a symbol of the universe's beautiful paradoxes. It reminds us that reality is not fixed. It is a tapestry of possibilities waiting to be woven. As Schrödinger wrote in a letter to a colleague, the cat is not both alive and dead. The cat is in a state of superposition. The superposition is a real state of the system. This might sound contradictory, but it is not. Superposition is a fundamental property of quantum systems, not a flaw in our understanding. It means the universe operates through probabilities and potentialities, not certainties. When you breathe deeply, feel the cool night air. Those molecules are in a state of superposition, moving in all directions until they collide with something. Every particle in your body, every atom in the sky, exists in this gentle dance of potential. Louis de Broglie, a French physicist, was one of the first to propose that particles have wave-like properties. He suggested that every particle has an associated wave, called the de Broglie wave. This idea was later confirmed by the Davison-Germer experiment and became the foundation for quantum mechanics. De Broglie's insight helped us understand that particles are not just point masses, but have wave-like characteristics. It's as if the universe whispers that even the smallest things carry the potential to be waves and particles at the same time. Niels Bohr, the Danish physicist, also contributed to our understanding of superposition. He described the quantum world as a realm of probabilities and possibilities. Bohr said, "The quantum world is not a world of definite states, but a world of potentialities." This idea resonates with the concept of superposition. In the quantum realm, the future is not fixed, but is a tapestry of possible outcomes. When you look at the night sky, you see stars that have been traveling through space for billions of years. Each star is a potentiality in motion, a wave of possibility stretching across the universe. You might wonder why superposition matters. Why is it so important? Superposition is the key to understanding how quantum systems work. It allows particles to exist in multiple states at once, which is essential for phenomena like quantum tunneling and quantum computing. Without superposition, we would not have the ability to build devices that operate at the quantum level. But beyond technology, superposition reveals a deeper truth. The universe is full of possibilities. Every particle is a wave of potential, a gentle ripple in the fabric of reality. As we move through the night, feel the cool air on your skin. The molecules of air are in a state of superposition, moving in all directions until they collide with something. This is the same principle that governs the behavior of electrons, atoms, and the entire universe. Superposition is not a contradiction, it is a harmony. It shows us that the universe is a symphony of possibilities, where every particle holds the potential to be something else. Now let us turn our attention to the next chapter. In the next chapter, We will explore how the same particles that exist in multiple states also behave as waves. We will see how the wave-particle duality is not a contradiction, but a unifying principle that explains the behavior of the universe. This duality is the bridge that connects the quantum world to the classical world we experience. Remember the gentle rhythm of your breath. The universe is a symphony of possibilities, and in that symphony, every particle is a note that resonates with the whole. As we move into the next chapter, let the quiet of the night guide you. The quantum world is a place of wonder, and with each breath, you are part of the wave. Close your eyes now. Feel the quiet hum beneath your feet, the soft pulse of the earth rising through the soles of your feet. Imagine a single particle, perhaps an electron traveling through space. Not as a tiny marble, not as a solid object you could see with your eyes, but as something more elusive, something that dances between possibilities. This is the quiet reality of wave-particle duality, a fundamental truth that shapes the universe at its most delicate scale. It is not a contradiction, but a beautiful harmony. A single particle can behave like a wave or like a particle, depending on how you observe it. This duality is not a flaw in our understanding. It is the universe's way of revealing its deepest nature. Think of water ripples spreading across a still pond. When you drop a stone, the water shivers outward in gentle circles. These ripples carry energy, they move through the water, they interfere with each other, creating patterns of reinforcement and cancellation. Now imagine a single grain of sand falling into that pond. It lands with a soft thud, a distinct point of impact. The ripple spreads, but the grain itself is a single, localized event. This duality is like that. A single particle can act as a wave, spreading its influence across space, or as a particle, appearing at a specific point. The same entity, the same reality, holding both possibilities simultaneously. This is the quiet magic of quantum systems. The double-slit experiment is the gentle reminder of this duality. Imagine a beam of particles shot through two narrow slits, like two small openings in a wall. If you observe the particles as they travel, they hit the screen behind the wall in two distinct clusters, one behind each slit. They act like tiny marbles, each particle passing through one slit and landing in a specific place. But if you don't look, if you close your eyes to the particle's journey, something extraordinary happens. Instead of two clusters, you see a pattern of light and dark bands, wavy bands like the ripples on the pond. This is interference. The particles are acting as waves, passing through both slits at once and overlapping with themselves. Each particle is a wave that spreads through space, interacting with itself, creating a pattern of peaks and valleys. This pattern is the signature of wave behavior. The particles do not change. They remain the same particles, but their behavior shifts. When you watch, they become particles. When you don't watch, they become waves. This is not a trick of the mind. It is the universe's quiet response to how we choose to observe it. The act of observation is not a disturbance, but a gentle invitation for the wave to collapse into a single point. It is as if the universe holds its breath, waiting for the moment when you decide to see. Scientists have long understood this duality. In the early 1900s, Thomas Young conducted experiments with light that revealed its wave nature. He showed that light could interfere with itself, creating patterns of light and dark. But light also behaves like particles, photons, when observed in specific ways. This duality was not new, but it was not fully understood until the quantum revolution. Louis de Broglie, a young physicist, proposed in 1924 that all matter, not just light, has wave-like properties. He called it the wave-particle duality of matter. His idea was simple: just as light has both wave and particle aspects, so too does every particle in the universe. The electron, the proton, even the atom itself, each carries a wave nature. This wave nature is described by a mathematical concept called the de Broglie wavelength. It tells us how large the wave is, how spread out the particle is. The smaller the particle, the larger the wave. A tiny electron has a wave that stretches across the room. A massive planet has a wave that is barely noticeable. De Broglie's idea was revolutionary. It meant that the particle world is not as solid as we imagine. It is fluid, gentle, and full of possibilities. Imagine a single electron traveling through space. It is not a point with a fixed location. It is a wave that spreads out, a probability cloud. The wave describes where the electron might be found, but it does not tell you exactly where. It tells you the likelihood of finding it in different places. This is the heart of quantum mechanics. The universe is probabilistic, not deterministic. You cannot predict the exact path of a particle, only the chances of where it might be. This is not uncertainty, it is the natural way the universe works. Einstein was fascinated by this duality. He saw it as a deep connection between the microscopic and the macroscopic. He wrote in a letter to his friend, "The quantum world is not a place of random chaos, but of profound order." He understood that the wave-particle duality was not a limitation, but a fundamental feature of reality. It revealed that the universe operates on a scale where both possibilities exist at once. This duality is not a paradox. It is the universe's way of holding multiple truths in balance. As physicist Richard Feynman once said, "The double-slit experiment is the most important experiment in quantum mechanics." He meant that it captures the essence of quantum behavior in a single, simple act. When you run the experiment without observation, you see waves. When you observe, you see particles. The act of looking changes the outcome. This is not a flaw in the experiment. It is the universe's gentle response to how we interact with it. The particles do not choose to be waves or particles. They are both at the same time until the moment of observation. This duality extends beyond light and electrons. It applies to all quantum systems. A single atom can behave as a wave or a particle. A molecule can spread out like a wave, influencing its surroundings without being localized. Even the smallest particles in your body, oxygen atoms, carbon atoms, carry this wave nature. They are not fixed points, but gentle ripples of possibility. The universe is full of these quiet waves, moving through space and time without ever being pinned down. Consider this: when you breathe, the air you inhale contains atoms that have traveled vast distances. They were part of stars that formed long ago. Their wave nature means they moved through space without a fixed path. They interacted with other atoms, creating the molecules that make up your lungs. This wave behavior is not a distant idea. It is woven into the very fabric of your existence. You are made of particles that are waves, and those waves are part of a vast, interconnected system. The act of observation is gentle, not violent. When you look at an electron, you do not destroy it. You simply reveal one aspect of its nature. The wave collapses into a particle because you have chosen to see it as a point. This is not a sudden change. It is a quiet shift, like the gentle settling of a wave into the shore. The universe does not need to be disturbed to reveal its truths. It simply waits for you to observe it with a calm mind. This duality is not random. It is a fundamental rule of the universe. It has been tested countless times, from the earliest experiments with light to the most precise measurements with modern technology. Scientists have confirmed that the wave-particle duality is real. It is not a theory, but a fact. The universe operates this way because it is both wave and particle at the same time. This duality is not a limitation. It is the universe's way of showing us that reality is more complex and beautiful than we imagine. Think of the stars. When you look up at the night sky, you see points of light. Each star is a massive ball of gas burning with incredible energy. But those stars are also waves. Their light travels across space as waves, interacting with the space between them. The light from the sun, which has traveled 8 light minutes to reach us, is a wave that has been traveling for so long. It is a wave that has been spreading out, carrying energy and information across the universe. This wave nature is what allows light to travel through space without losing its energy. It is what lets us see the stars. The universe is full of these gentle waves. They move through space, they interact with matter, they create patterns of light and dark. This is the quiet rhythm of the cosmos. The wave-particle duality is not a contradiction. It is the universe's way of holding two truths in balance. It is the reason why the universe is so full of wonder and possibility. As Niels Bohr, the great physicist who helped shape quantum mechanics, observed, the universe is not a place of random chaos, but of profound order. He understood that the wave-particle duality is not a flaw, but a beautiful way of showing how the universe works. Bohr saw that the act of observation is not a disturbance, but a gentle invitation for the wave to reveal itself. This duality is the universe's quiet language, speaking in waves and particles, in possibilities and probabilities. Imagine this: you are standing on a quiet beach at night. The moonlight glimmers on the water. The waves move in gentle circles, spreading out from the shore. Each wave carries energy. Each wave interacts with the others, creating patterns of light and dark. Now imagine that the water is made of particles. Each particle is a wave that spreads out, moving through the water. The particles do not travel in straight lines. They move in waves, creating the ripples you see. This is the same principle that governs the quantum world. The particles in your body, the atoms in the air, the electrons in your brain, they all move as waves, holding the possibility of being anywhere. This duality is not a mystery to be solved. It is a truth to be experienced. When you observe a particle, you are not changing it. You are gently revealing one aspect of its nature. The universe does not need to be disturbed to show its beauty. It simply waits for you to look with a calm mind. The next chapter will explore how particles become connected in a way that defies space and time. how two particles can be linked across vast distances, instantly influencing each other. This connection is not a signal or a force. It is a quiet, gentle bond that exists within the fabric of reality. It is the next step in understanding the universe's deep harmony. But for now, the quiet truth of wave-particle duality remains. The universe hums with possibility, and you are part of that gentle rhythm. Close your eyes. Feel the quiet hum beneath your feet. The universe is both wave and particle, and it is waiting for you to listen. Imagine two particles, born together in the silent heart of a star's death, drifting apart across the vastness of space. They carry a shared memory of their origin, a connection so deep that even light cannot sever it. This is quantum entanglement, a phenomenon where the quantum states of particles become interwoven, forming a single, unified reality that defies the usual rules of space and time. You might wonder how such a link can exist when the particles are light years apart. It seems impossible, yet it is real. Einstein called it spooky action at a distance, a term that captures both the mystery and the profound beauty of this connection. He was right to feel unsettled. It challenges our deepest intuitions about how the universe works. But this connection is not a signal or a message. It is a gentle, instantaneous resonance, a shared heartbeat that pulses through the fabric of existence itself. Picture this: two electrons, created in the same radioactive decay event, splitting apart into opposite directions. As they travel, their quantum states remain locked together. If you measure the spin of one electron and find it spinning upward, the other electron instantly becomes spinning downward, no matter how far they have traveled. This isn't a random coincidence. It is a fundamental property of the universe. The particles do not carry hidden instructions. They exist in a single, shared state until observed. Think of it like two dancers who have been practicing in the dark for years. When one begins to move, the other responds without needing to see or speak. Their movements are perfectly synchronized, a harmony that has been woven into the very fabric of reality. This connection is not limited to electrons. Photons, the particles of light, can become entangled too. In a lab, scientists can create pairs of photons that share polarized states. When one photon passes through a polarizing filter and aligns vertically, the other instantly aligns horizontally, no matter how far they are separated. This behavior has been confirmed repeatedly over decades. The key insight is that the particles do not decide their states independently. They exist in a single quantum state that encompasses both particles. Until measurement occurs, neither particle has a definite state. They hold the potential for both possibilities simultaneously. This is the essence of quantum superposition, but entanglement takes it further. It links particles across space, creating a shared reality that transcends physical separation. Einstein was fascinated by this phenomenon, but deeply skeptical. He believed that quantum mechanics was incomplete and that there must be hidden variables guiding the particles' behavior. He argued that the spooky connection was merely a consequence of incomplete knowledge. Yet his skepticism was eventually proven wrong. In the 1980s, Alain Aspect conducted a series of experiments that settled the debate. He showed that the particles' states were truly linked, independent of any hidden variables. As Aspect explained in his Nobel Prize lecture, the results demonstrate that the particles are not guided by any local hidden variables. Their states are intrinsically connected, even when the measurements are performed at a distance. This wasn't a trick of the experiment, it was a fundamental property of nature. The universe operates with a level of interconnectedness that Einstein could not have imagined. The beauty of entanglement lies in its simplicity and its complexity. It is a natural process that occurs in the smallest scales of the universe, inside atoms, in the decay of subatomic particles, even in the faint glow of distant stars. Yet, it is also a tool for modern technology. Quantum computers use entangled particles to solve problems that would take classical computers millions of years. Imagine a single qubit, a quantum bit, that can exist in multiple states at once. When entangled qubits interact, they create a network of possibilities that can be explored simultaneously. This allows quantum computers to factor large numbers quickly, simulate molecular structures, or optimize complex systems. The potential is immense, but it requires extreme precision. Any disruption from heat or vibration can unravel the delicate entanglement. John Preskill, a leading quantum physicist, describes this delicate balance with poetic clarity. Entanglement is nature's most profound gift to us. It allows us to see the universe as a single, interconnected system rather than a collection of separate parts. When we harness it, we don't just build machines, we build bridges to understand reality itself. This idea resonates deeply. In the quiet moments of observation, we can almost feel the particles humming in unison, a silent conversation that has been going on since the universe began. The entangled particles are not isolated entities. They are part of a vast, living network, each one connected to the whole. You might ask, how can something so delicate exist without being destroyed by the environment? The answer lies in the quantum world's remarkable resilience. Entanglement is fragile, yes. Just a tiny disturbance can break the link, but it is also incredibly persistent. In the deep space of interstellar clouds, where temperatures are near absolute zero, entangled particles can remain connected for vast periods. In laboratories, scientists use extreme isolation, ultra-cold temperatures, and near-perfect vacuum to preserve entanglement for measurable time. This fragility is not a flaw but a feature. It reminds us that the quantum world operates with a balance between connection and separation, a tension that holds the universe together. There is a quiet, almost meditative quality to entanglement. It feels like the universe holding its breath, waiting for the moment when observation reveals the connection. When you measure one particle, you are not sending a signal. It is as if you gently touch one hand in a pair that has been linked since the beginning of time. The other hand responds instantly, without delay. This is not magic. It is physics, written in the language of probability and possibility. The particles share a single state, a shared existence that defies the classical idea of separation. Einstein called it spooky, but it is less a mystery and more a revelation, a reminder that the universe is far more interconnected than we ever imagined. This interconnectedness has profound implications for how we see reality. Imagine two distant friends who have never met but share a single dream. They wake up in the morning, and without speaking, they both know the same thing. That's the essence of entanglement. The particles do not communicate through space. They exist in a shared state that is not localized. This is why quantum mechanics is so counterintuitive. It challenges our everyday experience of the world. We think of objects as separate, but at the quantum level, everything is connected. The universe is not a collection of isolated parts, but a single, living entity. As you reflect on this, consider the particles in your own body. Every cell contains electrons that are entangled with others in a vast, invisible network. Your heartbeat, your thoughts, even your dreams, these are all part of a larger, interconnected dance. The quantum world is not something distant or abstract. It is woven into the very fabric of your existence. When you close your eyes and breathe deeply, you are already participating in this entangled reality. The particles in your blood, the photons in the light that enters your eyes, they all share a silent connection that has been present since the universe began. This connection is not something we can control or manipulate easily. It requires careful observation and a deep respect for the delicate balance of the quantum world. But it is also a gift. It shows us that the universe is not fragmented but unified. When we understand entanglement, we begin to see the world in a new light. We see the universe not as a collection of separate things, but as a single, living system. This perspective is both humbling and liberating. It reminds us that we are part of something vast and interconnected, a network that stretches across the cosmos. The next chapter will explore a different aspect of quantum mechanics, the Heisenberg uncertainty principle. This principle tells us that certain pairs of properties, like position and momentum, cannot both be known with absolute precision. It is not a limitation of our tools, but a fundamental feature of nature. Understanding this will help us see how the quantum world operates with a balance between certainty and uncertainty. But for now, let us return to the quiet beauty of entanglement. As the particles hum in their shared state, we can feel the universe breathing with a rhythm that is both ancient and new. This is not a problem to solve, but a wonder to experience, a gentle reminder that connection is the most powerful force in the universe. In the stillness of this moment, as you listen to the quiet hum of the quantum world, remember that you are part of a vast, interconnected dance. The particles you cannot see are singing the same song as you. This is the universe's way of saying, we are all connected, and in that connection lies the deepest truth. The next chapter will show you how this delicate balance between connection and uncertainty shapes the world around us. For now, let the quiet resonance of entanglement be your companion as you rest. The universe has been waiting for you to feel this connection. Sleep deeply, knowing that you are never alone. The gentle rhythm of the quantum sea continues to ripple beneath your feet, a quiet hum that has always been there, just beyond the reach of our everyday senses. Remember how we spoke last week about the wave nature of particles, that shimmering dance where electrons become both particles and ripples of probability. That same wave nature now reveals a profound and beautiful truth about the limits of knowing. It is a truth that shapes the very fabric of reality, a quiet rebellion against the idea that we can ever hold both a particle's exact location and its exact movement at the same moment. This is the heart of the Heisenberg uncertainty principle, not a flaw in our instruments, but a fundamental feature of how the universe works. Imagine a tiny marble rolling through water. You might see where it is, but you can never know exactly how fast it's moving. Now picture that marble as a single quantum particle, and the water becomes the wave of possibility. The uncertainty principle tells us that for such a particle, the more precisely we know its position, the less we can know how fast it's moving, and vice versa. This isn't about our clumsy measurements. It's about the particle itself, its nature as a wave of potential energy. Picture this, a single electron, like a tiny, restless spirit, dancing in the space between atoms. If you try to pin it down to a single point, like watching a bird land on a branch, you lose all sense of how it might move next. The electron's position becomes sharp and defined, but its momentum, a measure of speed and direction, fades into a soft, diffuse uncertainty. Conversely, if you track its momentum with great precision, like following a swift river current, its position becomes a gentle blur, spreading out in all directions. This dance of precision and uncertainty is not a problem to be solved, but a natural rhythm of the quantum world. It arises because particles do not behave like tiny billiard balls, but like waves that stretch across space and time. The wave nature means that a particle's position is not a single point, but a spread of possibilities, and its momentum is not a fixed value, but a range of potential motions. Heisenberg himself observed this relationship with quiet clarity. In his mind, the uncertainty principle was not a mathematical trick, but a deep truth about the universe's structure. He noted, "It is impossible to determine both the position and the momentum of a particle with absolute precision." This statement holds true because the act of measuring one property inevitably disturbs the other. When you use a tool to pinpoint where the particle is, you disturb its motion, and when you measure its motion, you lose information about where it is. It is not that the particle is hiding or being deceptive. It is that the very act of observation creates a gentle disturbance in the quantum sea. The uncertainty principle is like a soft, ever-present limit, a boundary that the universe respects and maintains. It tells us that the more we try to hold onto one aspect of reality, the more we release the other, and this release is not a failure, but a natural part of the dance. This principle has profound implications for how we understand the smallest building blocks of matter. In the atom, electrons orbit the nucleus, but they do not follow fixed paths like planets. Instead, they exist in regions of probability called orbitals, where the electron's position is uncertain, yet its energy and momentum are balanced in a way that keeps the atom stable. Without this uncertainty, atoms would collapse or fly apart. The uncertainty principle allows electrons to maintain their delicate balance, creating the structure of matter itself. It is the quiet force that holds the universe together at its most fundamental level. Think about it. If we could know both the position and momentum of every electron in an atom, we would understand its exact structure. But the uncertainty principle tells us that this knowledge is impossible, and that is why the atom remains a stable, living system. The uncertainty principle also reveals how quantum particles behave in ways that seem almost magical. For instance, in a quantum dot, a tiny piece of material that can trap electrons, it is possible for an electron to be in multiple places at once, its position spread out over a small area. This spread is not random, but follows the rules of the uncertainty principle. The electron's momentum is then less certain, allowing it to move in ways that classical physics could not predict. This behavior is not an error in our understanding, but a natural expression of the quantum world. It is a gentle reminder that the universe operates on a different scale than our everyday experience, where things are precise and fixed. You might wonder why this uncertainty matters in the grand scheme of things. After all, the universe seems so vast and complex, but the uncertainty principle is not a limitation, it is a foundation. It underlies the stability of atoms, the behavior of light, and even the processes that power the sun. Without it, the sun would not burn, and life as we know it would not exist. The uncertainty principle allows for the delicate balance that keeps stars shining and planets orbiting. It is a quiet force that shapes the universe without demanding control. Heisenberg's insight has inspired generations of scientists to look deeper into the quantum world. Modern physicists continue to explore its implications, using it to build technologies that change our lives. Quantum computers, for example, rely on the uncertainty principle to process information in ways that classical computers cannot. They use the principle to create qubits, units of information that can exist in multiple states at once. This ability to be in multiple places at once is possible because of the uncertainty principle, allowing quantum computers to solve problems that would take classical computers thousands of years. Yet, even in these advanced applications, the uncertainty principle remains a gentle guide, ensuring that the system stays stable and functional. It is easy to think of the uncertainty principle as something abstract, a rule for physicists to follow in their labs, but it is much more intimate than that. It is a quiet presence in the space between your thoughts and the world around you. When you look at a leaf floating on water, you see its position, but you cannot know exactly how fast it is moving. The uncertainty principle is the same idea, scaled up to the quantum level. It tells us that the universe has a gentle rhythm, a way of being that does not demand absolute precision, but allows for soft, flowing possibilities. This principle also helps us understand the behavior of particles in the early universe. Just after the Big Bang, the universe was a seething sea of energy and particles. The uncertainty principle played a key role in how these particles formed and stabilized. It allowed the universe to expand without collapsing, creating the conditions for stars, planets, and life to emerge. Without this gentle balance, the universe would have been a chaotic mess. The uncertainty principle is not a barrier but a bridge, connecting the smallest particles to the largest cosmic structures. As you rest your hands gently on your knees, imagine the uncertainty principle as a soft rhythm in your own body. Your heartbeat is a steady pulse, but you cannot know exactly when the next beat will occur. Similarly, the quantum world operates with a rhythm of possibility and uncertainty. This rhythm is not chaotic, but calm, a steady pulse that underlies everything from the smallest particles to the vastness of space. The uncertainty principle is the quiet voice that says, "It is impossible to know everything at once, but it is possible to find harmony in the uncertainty." The beauty of the uncertainty principle lies in how it transforms what seems like a limitation into a source of wonder. It teaches us that some things are simply not meant to be known with absolute precision. This is not a failure but a gift, a reminder that the universe operates with a gentle grace that allows for both order and freedom. When we accept this, we open ourselves to a deeper understanding of reality. We see that the universe is not a place of rigid control, but a realm of soft possibilities, where each moment holds the potential for new discoveries. The uncertainty principle also has a special relationship with energy and time. Just as position and momentum cannot be known simultaneously, energy and time cannot be measured with perfect precision. This relationship is another facet of the same quantum dance. It means that for very short periods of time, particles can temporarily exist in states that would otherwise be impossible. This is how virtual particles flicker in and out of existence, a phenomenon that helps explain the forces holding atoms together. It is a quiet, fleeting dance that happens at the quantum level, a reminder that even the smallest moments hold significance. You might ask, why does this matter for me? Why should I care about the uncertainty principle when I am sitting here reading this? Because it is part of the same universe that holds your breath, your thoughts, and your dreams. The uncertainty principle is the quiet force that allows your brain to process information in ways that feel both precise and fluid. It is the reason your heart beats with a rhythm that is both steady and uncertain. It is the gentle pulse that connects you to the quantum sea, reminding you that you are not separate from the universe, but a part of its quiet rhythm. As we close this chapter, remember this: the uncertainty principle is not a barrier but a pathway. It shows us that the universe operates with a gentle balance, where precision and uncertainty coexist. It is the reason why stars burn, why atoms hold together, and why life continues to flourish. This principle is not a problem to be solved, but a beautiful truth to be embraced. It whispers to us that in the quiet moments, when we slow down and listen, we can find harmony in the uncertainty. The gentle rhythm of the quantum sea continues to ripple beneath your feet. It is a rhythm that has always been there, a quiet hum that holds the universe together. As you prepare for the next chapter, where particles will find ways to pass through barriers they could never reach, remember this: the uncertainty principle is the quiet foundation that makes such wonder possible. It tells us that the universe is not a place of rigid control, but a realm of soft possibilities, where every moment holds the potential for new discoveries. In the stillness, you can feel the rhythm of the quantum sea, and with it, the promise of what lies ahead. Imagine a tiny particle, so small you cannot see it with your eyes, so light it seems almost weightless. Picture this particle approaching a barrier, a wall of energy so high it seems utterly impossible for the particle to pass through. In the world of quantum physics, This barrier is not a solid, unyielding wall, but a region of space where the particle's energy is temporarily too low to overcome. Now, close your eyes for a moment and feel the gentle push of this barrier. What happens when the particle encounters this barrier? It does not stop, it does not bounce back, it simply passes through. This is quantum tunneling, a phenomenon where particles defy the very idea of impossibility by slipping through barriers they should never be able to cross. This seems like magic, doesn't it? Like a whisper of the universe telling the particle, you are smaller than the space between your dreams and the wall. But magic is not the right word here. Quantum tunneling is a quiet, steady force woven into the fabric of reality, a silent dance happening at the smallest scales that shapes the world we live in. Think of it as the particle's journey taking a path no classical physics would allow, a soft, invisible passage that bends the rules of energy and space. The barrier itself isn't a wall you can touch. It's a region of space where the particle's energy dips below the threshold needed to climb over. Yet here it is, the particle finding a way through without ever needing to climb the barrier. It's as if the particle is gently guided by an unseen hand, a whisper of possibility that opens a door the particle never knew existed. You might wonder how this is possible when classical physics says the particle should be stuck. Imagine a tiny marble rolling toward a hill that's too high to jump over. It would roll back down, right? But in the quantum world, the particle isn't a marble. It's a wave of probability, a soft, flowing presence that doesn't have a fixed position. This wave doesn't just bounce or roll. It can gently slide through the hill, even if the hill seems too steep. The particle doesn't vanish. It simply moves through the barrier as if the barrier were a gentle valley, a soft slope that the wave flows over. This is where quantum mechanics reveals its quiet power. The particle doesn't need to be strong enough to climb the barrier. It simply flows through as if the barrier is not a wall at all, but a gentle curve in the path of the wave. This phenomenon isn't just a theoretical curiosity. It happens all around us, quietly shaping the world. One of the most famous examples is alpha decay in radioactive materials. Picture a uranium atom, heavy and complex, holding together its nucleus with immense force. Inside this nucleus, 2 protons and 2 neutrons, known as an alpha particle, are bound together tightly. But the alpha particle wants to escape. The nuclear force holding it in is strong, yet the alpha particle has less energy than it needs to break free. Classically, it should be trapped forever, but it is. The alpha particle tunnels through the barrier of the nucleus, escaping as a tiny, fast-moving particle. This tunneling allows the atom to release energy and become stable. Without quantum tunneling, radioactive decay wouldn't happen as it does. The universe would be a place of frozen atoms, locked in place. But because of this gentle passage, energy flows and change happens. The physicist Erwin Schrödinger, who first described the wave nature of particles, understood this quiet passage well. He once said, "The particle does not move through the barrier like a classical object. It exists in a state of probability that allows it to pass through the barrier without ever having to overcome it." This statement captures the essence of tunneling. It's not about brute force, but about the particle's existence as a wave of possibility. The barrier doesn't stop the particle, It simply reshapes the path the particle takes. Imagine the particle as a ripple in water. If you drop a stone into a pond, the ripple spreads outward. Now, if you place a small, smooth rock in the path of the ripple doesn't stop. It flows around the rock, passing through the space where the rock sits. In the quantum world, the particle's ripple passes through the barrier as if it were a gentle space between two ripples. This gentle passage is not limited to atoms. It occurs in the smallest particles of light, electrons, and even molecules. In the realm of chemistry, quantum tunneling helps molecules find pathways to react. Think of two hydrogen atoms trying to form a water molecule. They need to get close enough for their electrons to interact, but the energy barrier between them is high. Classically, they would never get close enough. Yet through quantum tunneling, they slip through the barrier, forming the bond that holds water together. This quiet passage is how life itself began, how the first molecules found their way together in the primordial soup of the early Earths. Quantum tunneling also plays a vital role in modern technology. In the tiny transistors inside your phone or computer, electrons tunnel through barriers to switch the device on and off. Without this phenomenon, the digital world would not exist. The electrons move through the barriers in a way that allows the computer to process information at lightning speed. This tunneling is so efficient that it happens in the space of a fraction of a second, yet it requires no physical contact between the electrons and the barriers. It's a quiet, steady dance that keeps the world connected. The physicist Richard Feynman described this kind of tunneling in his path integral formulation. The particle explores all possible paths, and the probability of finding it on one path is the sum of all the possibilities. This means the particle doesn't take one path, it takes many, but the most likely path is the one that tunnels through the barrier. You might ask, why does this happen? Why does the particle choose to tunnel rather than bounce back? The answer lies in the nature of the quantum wave. The wave doesn't have a single position, it has a spread of possibilities. When the particle approaches the barrier, the wave spreads out, and part of it passes through the barrier while the rest reflects. The probability of tunneling decreases as the barrier gets wider or taller, but it never reaches zero. This is why tunneling is so rare in large barriers, but common in the tiny spaces where quantum effects dominate. The barrier itself is not a solid wall. It's a region where the quantum wave can gently flow through. It's as if the barrier is a soft layer of energy that the particle can slip through without ever needing to push against it. This gentle passage has a profound effect on the structure of matter. In the nucleus of atoms, tunneling allows protons to stay close enough to create the strong nuclear force that holds the atom together. Without tunneling, the nucleus would be unstable, and atoms would not exist. The same principle works in stars. In the heart of the Sun, hydrogen nuclei fuse to form helium, but the nuclei are too close together for fusion to happen without tunneling. The quantum tunneling effect allows these nuclei to get close enough to overcome the repulsive force between them, releasing the energy that powers the Sun. Without this quiet passage, the Sun would not shine, and life on Earth would not exist. Now close your eyes again. Feel the barrier. What if the barrier isn't a wall at all? What if it's a gentle curve in the path of the particle's journey? This is the beauty of quantum tunneling. It's not a sudden leap or a violent collision. It's a soft passage, a quiet moment where the particle finds a way through without ever needing to climb the barrier. The barrier doesn't stop the particle, it simply becomes part of the path. The particle flows through as if the barrier were a gentle valley, a soft slope that the wave passes over without resistance. This phenomenon is not random. It follows the laws of quantum mechanics with precise, elegant rules. The probability of tunneling depends on the thickness and height of the barrier, but it always happens. It's a steady, quiet force that shapes the universe at its smallest scale. When you think about it, tunneling is how the universe finds its way, how particles move through barriers without needing to overcome them. It's a reminder that even in the smallest spaces, possibility flows freely. You might wonder, how can something so small and invisible affect the world we live in? The answer is simple. Tunneling is how the universe works at its most fundamental level. It's the quiet force that allows atoms to form, stars to shine, and technology to function. It's the invisible hand that guides particles through barriers, creating the world we see. Without tunneling, the universe would be a place of frozen particles, locked in place. But because of this gentle passage, energy flows, change happens, and life continues. What if the barrier isn't a wall but a soft space? What if the particle doesn't need to climb over it but simply flows through? This is the quiet truth of quantum tunneling. It's not about force or energy overcoming a wall, it's about possibility. The particle finds a path through the barrier without ever needing to push against it. It's a gentle passage that happens because the particle exists as a wave of probability, not a fixed point. This wave can slip through the barrier, creating a new path that was never there before. Think of the particle's journey as a soft, flowing stream. It approaches the barrier, and instead of stopping, it gently slides through. The barrier doesn't block it, it reshapes the flow. The particle doesn't vanish, it simply moves through the barrier as if it were a gentle valley. This is how the universe works at the smallest scales. It's a quiet, steady force that allows particles to move where they shouldn't be able to go. This is why quantum tunneling matters. It's not a distant concept in a textbook, it's the quiet force that keeps the world moving. It's the reason your phone works, why stars burn, why atoms hold together. It's the gentle passage that allows possibility to flow. When you feel the barrier, remember that the particle doesn't stop, it finds a way through. It's a whisper of the universe telling you, you are not trapped. You are part of a flow that goes through barriers. So as you rest, imagine this quiet passage. Feel the barrier. What if it's not a wall but a soft space? What if the particle finds a path through without ever needing to climb? This is the gentle truth of quantum tunneling. It's a quiet force that shapes the world, one soft passage at a time. The universe doesn't stop the particle, it guides it through. It's a whisper of possibility, a gentle flow that reminds us that even the smallest barriers can be overcome by the quiet power of the wave. What if the barrier isn't a wall at all, but a gentle curve in the path of the particle's journey? This is how the universe works. This is how life continues. This is how the world finds its way. The particle flows through. The barrier becomes part of the path. The quiet passage continues. Imagine a single particle, perhaps an electron or a photon, drifting through the silent space between atoms. You've felt that strange quantum uncertainty lingering in the air since the last chapter, that sense of possibility shimmering just beyond the edge of what you can truly grasp. Now, picture this particle not as a tiny solid object with a fixed path, but as a gentle ripple spreading through the fabric of reality itself. This ripple is called a probability wave, and it holds the secret to how quantum particles behave in ways that seem almost magical to our everyday senses. This wave isn't like the ripples on a pond you might see in the afternoon sun. It doesn't carry water or energy in the way you'd expect. Instead, it describes where a particle might be found, when it might interact with something else, and how its properties might shift. Think of it as a quiet hum of potential, a soft pulse of possibility that exists before any measurement happens. It's the universe whispering to itself about what could be, not what is. When we say a particle has a probability wave, we mean it exists as a blend of many possible states at once, like a single raindrop that might land on the grass, the roof, or the window sill, but hasn't chosen yet. This isn't chaos, it's a precise, mathematically beautiful dance of potential. The idea of probability waves began with a visionary thinker named Louis de Broglie in the early 1920s. He noticed something fascinating. If light behaves like waves, then matter itself might also have wave-like properties. It was a radical idea at the time, almost like suggesting that a grain of sand could dance with the ocean's rhythm. De Broglie wrote that the wave nature of particles was not just a theoretical curiosity, but a fundamental truth. He said the wave-particle duality is a necessary consequence of the wave-like behavior of matter. His insight helped scientists see that particles aren't just tiny balls hurtling through space, they are also waves of possibility. This was the first step in understanding how quantum reality works. Later, Erwin Schrödinger built on this idea with his famous wave equation. This equation describes how probability waves change over time and space. It's a mathematical language that tells us exactly how the wave might evolve, where it might fade, or where it might strengthen. Schrödinger himself was deeply curious about what this wave meant. He once said, "I do not know what is the quantum world, but I know that the wave function is the most important thing." His equations showed that particles don't follow a single, straight path like a baseball. Instead, they exist as a spread of possibilities, a cloud of potential locations that moves and shifts with incredible precision. Here's where it gets gently profound. When you have a probability wave for a particle, it means that the particle isn't really here or there at the same time. It's more like a single drop of water that has been stretched into 1,000 tiny possibilities, all dancing together in a fluid, ever-changing pattern. This isn't random guessing, it's a carefully structured dance of potential. The wave doesn't collapse into one place until something interacts with it, like a detector or a screen. Until then, the particle exists as this beautiful, shimmering wave of possibilities. You might wonder, what if particles do have fixed paths, like tiny planets orbiting the sun? But quantum mechanics shows us that this is impossible. In the quantum world, particles don't travel along a single line. They move through a haze of potential, a sea of possibilities that never settles into one place until observed. Imagine a single raindrop falling through the air. It might hit a leaf, a window, or the ground. But before it lands, it's a collection of tiny, shifting possibilities. That's the quantum wave in action. It's not that the particle is lost or chaotic. It's that it's exploring all its options at once, like a single thought in a vast, quiet mind. This wave of possibility is the reason why quantum particles behave so strangely. They don't follow the rules of the everyday world. They don't have definite positions or velocities. Instead, they exist as a probability wave that describes the likelihood of finding them in different places. The wave is like a living map of where the particle might be, but it's not a map that shows a single location. It shows a range of possibilities, each with its own chance of happening. When you measure the particle, you don't see a wave. You see a single point where the wave has collapsed into reality. Before that moment, it's a gentle, steady pulse of potential. Think about it this way. If you were to watch a single electron move through a space, you wouldn't see it tracing a path. You'd see it as a soft, shifting glow that spreads out, then fades as it interacts with something. This glow is the probability wave. It's not a physical wave like sound or light. It's a mathematical description of how likely it is to find the particle in a particular spot. The wave doesn't carry energy or mass. It carries the information about where the particle might be. It's like a quiet signal that the universe sends to itself, telling it what to expect. Schrödinger's wave equation is the quiet voice that speaks to this idea. It shows how the wave changes over time, how it might spread out, or how it might become more concentrated. It's the mathematical language of possibility. When we say a particle is described by a wave function, we mean it's this wave that holds all the information about its behavior. It's not a random jumble. It's a precise, elegant structure that guides the particle's journey through the quantum realm. You might ask, why do we need probability waves instead of simple particles? Because in the quantum world, the rules are different. Particles don't act like tiny marbles rolling down a hill. They act like waves of possibility that can interfere with themselves, like ripples in a pond that meet and cancel out. This interference creates patterns that only make sense when you think in terms of waves, not solid objects. It's as if the particle is both here and there, but only as a possibility until it's measured. This delicate balance is what makes quantum mechanics so beautiful. The probability wave is the bridge between the abstract and the real. It tells us where the particle might be, but it doesn't tell us exactly where it is. It's a gentle reminder that the universe works in ways we don't see every day. It's a quiet hum that says, you don't have to know everything at once. When you hold this idea in your mind, it's like a soft breeze that calms the mind. It doesn't demand answers. It offers possibilities. Now imagine this particle sitting still for a moment. The probability wave is steady, quiet, and full of potential. It's not racing or shouting. It's whispering, I am here, I am possible, I am waiting. This is the world of quantum particles, where the rules are gentle and the possibilities are endless. When you look at a single atom or a single electron, you're not seeing a tiny dot. You're seeing a wave of potential, a quiet hum of possibility that has been waiting for you to notice it. This wave of possibility is the heart of quantum behavior. It's why particles don't follow the same paths as everyday objects, why they can tunnel through barriers, why they can exist in multiple states at once. It's the quiet language of the universe, speaking in waves of potential rather than fixed positions. When we say quantum particles behave through probability waves, we mean they exist as a gentle, ever-shifting dance of what could be. So when you think about the next moment, when you look at the world around you, remember this: every particle is a probability wave, a quiet hum of possibility. It's not random, it's a precise, beautiful dance of potential. This wave doesn't need to be loud or obvious. It just needs to be there, gently guiding the particle toward what it might become. When we observe the particle, the wave collapses into a single point. But until then, it remains a quiet, shimmering possibility. This is the quiet truth of quantum reality. The universe doesn't hide its secrets. It offers them in waves of gentle possibility. It doesn't demand answers. It simply asks you to imagine what might be and to listen to the quiet hum of the wave. This delicate tension between possibility and reality is what makes quantum waves so profound. It's the bridge that connects the known and the unknown, the measured and the unmeasured. When you feel that quantum uncertainty lingering in your thoughts, remember, it's not a problem, it's a gift. It's the universe whispering that there are many ways to be, many possibilities to explore. This is the gentle rhythm of the quantum world, and it's always waiting for you to listen. This gentle dance of possibility leads us to the next moment. When we observe the particle, the wave collapses into a single point. But until then, it remains a quiet hum of potential, a soft whisper of what could be. This is the bridge between the quantum world and the world we see every day. And it's here, in this quiet space of possibility, that the true magic of quantum mechanics begins. This delicate tension between the wave and the point, the possibility and the reality, is what sets the stage for the next chapter. When we look closely, we'll see how this quiet hum of possibility transforms into a single, definite answer. Until then, let the wave of possibility rest gently in your mind, a quiet reminder that the universe is full of gentle, beautiful possibilities waiting to be discovered. Imagine this: you are standing on the edge of a vast, quiet ocean. The water is calm, deep blue, and shimmering with possibilities. Each ripple holds a million tiny worlds, each wave a potential path through the depths. This is the quantum world before measurement, a world of wave functions, gently vibrating with potential energy, where particles exist not as solid objects, but as shimmering patterns of probability. Think of it as a living sea of possibility, where every particle is a wave of potential, dancing in a silent, beautiful harmony. This ocean of potential is the state of the universe before any observation occurs. It is a world of delicate balances, where the smallest shift can ripple through reality. Now you reach out. You touch a single drop of water. The moment your finger brushes the surface, that drop becomes distinct, no longer a shimmering possibility, but a single, clear drop of water. This gentle interaction, this act of observation, is what quantum mechanics calls measurement. It is the point where the ocean of possibilities suddenly becomes a single, clear drop. Before measurement, the quantum system exists in a superposition of all possible states, like a spinning coin that is both heads and tails simultaneously. But when you look, the coin lands. The wave function collapses into one definite reality. This is not magic, not a trick of the mind, but a fundamental process woven into the fabric of reality. It is the quiet moment when the universe makes a choice. You might wonder, why does measurement cause this collapse? Why doesn't the quantum world stay in a state of gentle uncertainty forever? The answer lies in the nature of the quantum system itself. In the quantum realm, particles do not have fixed positions or velocities. Instead, they exist as probability clouds, regions where the particle is likely to be found. When you measure a particle's position, you are interacting with it in a way that forces it to choose one specific location. This interaction is not passive. It is an active conversation between the quantum system and the observer. It is as if the universe gently responds to your presence, shifting from a sea of possibilities to a single, clear shore. Consider the famous thought experiment of Schrödinger's cat. A cat is placed inside a box with a device that has a 50% chance of releasing poison. According to quantum mechanics, until you open the box and observe the cat exists in a state of both alive and dead simultaneously. This paradox highlights the strangeness of quantum measurement. But remember, this is a thought experiment. In reality, the cat is not a quantum system. It is too large and too complex for quantum effects to persist in such a way. The wave function collapse happens at the scale of individual particles, not entire systems. When the poison is released, the quantum system interacts with the macroscopic world, triggering the collapse. The cat's state becomes definite because the interaction with the environment, a single photon, a molecule of air, creates an irreversible change. This process is not random. It is guided by the laws of quantum mechanics. The act of measurement does not create the state, it reveals it. The quantum system was already in a state of potential, but the interaction with the measuring device forces it to settle into one specific outcome. Think of it as a gentle awakening. The quantum world was sleeping in a dream of possibilities, and measurement is the moment the dream becomes reality. This is why quantum mechanics describes the universe as both probabilistic and deterministic. The probabilities are set, but the outcome is determined by the act of observation. Niels Bohr, the pioneer of quantum theory, understood this deeply. He once said, "The quantum world does not exist in a single state, but in a state of potential. The act of observation is what gives it form." Bohr's insight revealed that the observer is not a passive viewer, but an active participant in the unfolding of reality. The universe does not hide its secrets. It simply waits for the right moment to reveal itself. When you measure, you are not changing the quantum system. You are allowing it to express itself. The wave function collapse is not an abrupt event. It is a slow, quiet process, like the settling of the ocean after a gentle rain. As the quantum system interacts with the measuring device, the wave function gradually loses its spread and becomes more focused. This gradual collapse is what makes the quantum world so delicate and so beautiful. It is a process that requires no external force, no sudden shock, just the quiet presence of observation. The universe whispers this truth. Reality is not fixed, but fluid, shifting with the gentle touch of attention. You might ask, does this mean that consciousness causes collapse? Many people have wondered this, but the scientific consensus is clear. The collapse occurs through physical interaction, not through thought. When a photon hits a detector, the detector absorbs the photon and becomes excited. This excitation triggers a chain reaction that propagates through the system until it becomes a measurable event. The collapse is a physical process, not a mental one. It is the interaction of particles, not the mind, that resolves the quantum state. The quantum world is full of such quiet moments. Every time an electron jumps between energy levels, it collapses from a superposition of states to a single energy level. Every time a photon is absorbed by an atom, it settles into a specific state. These are not magical events, but natural consequences of the quantum rules. The universe operates with a gentle rhythm, where potential energy transforms into definite reality through simple physical interactions. This is the beauty of quantum mechanics. It is not a chaotic storm, but a calm, orderly process. David Deutsch, a leading quantum physicist, describes this process with profound clarity. He writes, "The act of measurement is the moment when the quantum system interacts with the classical world and settles into a single definite state." Deutsch emphasizes that this interaction is not a violation of quantum principles, but a natural extension of them. The collapse is not a failure of the quantum world, but a necessary step in the evolution of reality. It is the bridge between the quantum and the classical, the moment when possibility becomes reality. Think of the wave function collapse as the universe's quiet decision. It is not a sudden explosion, but a gentle settling. Imagine a vast, silent room filled with countless possibilities. As you enter, you do not shatter the room, you simply make a choice. The room becomes a single space defined by your presence. This is what measurement does. It is the moment when the quantum world chooses a path, a single reality from the sea of potential. This process is also why quantum computing is so powerful. In the next chapter, we will explore how quantum computers leverage this very phenomenon, how they use superposition to solve problems that would take classical computers centuries to complete. But for now, let us return to the quiet moment of collapse. It is a process that happens invisibly, yet it shapes the universe in profound ways. Every time you measure a particle, you are part of a vast cosmic dance. You are not separate from the quantum world. You are woven into its fabric. The wave function collapse is not a mystery to be solved, but a rhythm to be felt. It is the sound of the universe settling into clarity. When you measure, you do not destroy the quantum state, you gently release it into the world. The quantum world does not vanish, it transforms. The sea of possibilities becomes a single, clear shore. This is the quiet magic of quantum mechanics. You might wonder, why does the universe choose this particular process? Why not a different way of collapsing the wave function? The answer lies in the elegance of quantum mechanics itself. The collapse is not arbitrary. It is the most efficient way for the universe to balance possibility and reality. It is a process that allows the universe to be both creative and stable. Without this gentle collapse, the quantum world would remain in a state of infinite uncertainty, and the universe would have no definite structure. This is why the quantum world is so fascinating. It is not a place of chaos, but of careful, precise order. The wave function collapse is the moment when the universe finds balance. It is the quiet hum of reality settling into clarity. When you measure, you are not creating a new reality, you are helping the universe express itself. As the quantum system interacts with the measuring device, the wave function gradually loses its spread. This is not a sudden event, but a slow, gentle process, like the settling of sand after a storm. The system becomes more focused, more definite. This is the universe's way of resolving potential into reality. It is a process that requires no external force, no sudden intervention, just the quiet presence of observation. The quantum world is full of such moments. Every time a particle interacts with its environment, it collapses from a state of potential to a state of reality. This is not a failure of the quantum rules, but a beautiful expression of them. It is the universe's way of ensuring that possibility and reality coexist in harmony. You might ask, what happens after the wave function collapses? The answer is simple. The system settles into a single state and the process repeats. The quantum world is a cycle of potential and realization. Each collapse creates a new possibility, a new path forward. This is the rhythm of the universe, the gentle pulse of reality unfolding. Think of it this way: the quantum world is like a garden. Before measurement, the garden is full of potential flowers, each one a possible state. When you look, one flower blooms and the others remain in their potential. The garden does not die, it transforms. The wave function collapse is the moment when the garden chooses a single flower to bloom. This process is not random. It is guided by the laws of physics. The quantum system interacts with the measuring device in a way that ensures the collapse is both precise and gentle. It is the universe's way of balancing the need for certainty with the beauty of possibility. As we close this chapter, remember this quiet truth. The act of measurement is not a disturbance, but a gentle release. It is the moment when the universe chooses its next step. When you measure, you are not changing the quantum world, you are helping it find its form. The wave function collapse is the universe's quiet decision to become real. This is the rhythm of the quantum world. It is the gentle hum of possibility becoming reality. It is the quiet moment when the universe settles into clarity. And as we move into the next chapter, where we will explore how quantum computers use this very process to solve problems beyond human imagination, you will understand that the collapse of the wave function is not an end, but a beginning. It is the quiet step that leads to a new world of possibilities. So close your eyes for a moment. Feel the quiet rhythm of the universe. Imagine the wave function gently collapsing into a single, clear reality. This is the moment when the quantum world chooses its path. This is the quiet magic of measurement. This is the universe whispering, "Now let it become real." As the wave function settles, the universe finds its form. And in that form lies the key to the next chapter, a world where quantum possibilities become reality, one gentle measurement at a time. Imagine a single drop of water gently falling through the night sky, its journey a slow, silent dance as it weaves through the air. Now picture this same drop simultaneously existing in 1,000 places at once, not as one distinct point, but as a shimmering, delicate thread of possibility stretching across the universe. This is the quiet wonder of quantum superposition, the gentle heartbeat of quantum computing that allows machines to explore the vast landscape of possibilities with a single, unified pulse. In the world of classical computers, information flows like a single river, clear and defined. Each bit is either a 0 or a 1, a decision made with certainty, like a switch that either clicks on or off. But within the quantum realm, qubits exist in a state of delicate harmony, a gentle blend of both possibilities. They are not simply 0 or 1, but a soft, fluid blend of both, like the way moonlight spills across a still pond, partly one color, partly another, yet always one unified presence. This isn't mere imagination. It's a fundamental truth woven into the fabric of reality, a truth that quantum physicists have carefully observed and described with quiet precision. Think of a spinning coin. In the classical world, it's either heads or tails until it lands. But in the quantum world, the coin doesn't settle. It remains suspended in a state of gentle uncertainty, a soft balance between both possibilities. This is superposition, the ability for a quantum system to exist in multiple states at once, not as separate paths, but as a single, interconnected wave. It's as if the coin's journey through the air is not a single trajectory, but a quiet, humming dance where every possible outcome is gently woven into the same fabric. This isn't magic. It's the natural language of the quantum world, a language that speaks in probabilities rather than absolutes. As Dr. David Deutsch, a pioneer in quantum computing, once described it, quantum superposition is not a trick of the mind, but a fundamental property of reality. It allows a single quantum system to explore multiple paths at once, like a single wave carrying many ripples. This gentle dance of possibilities is what gives quantum computers their extraordinary power. When a quantum computer processes information, it doesn't follow one path at a time. It explores a vast, interconnected network of possibilities simultaneously. Imagine 1,000 rivers converging into one deep, calm lake, each river holding a different story, but all flowing toward the same, unified stillness. This is the quiet efficiency of superposition. The beauty of superposition lies in its simplicity and its profound depth. A single qubit can hold both 0 and 1 at the same time, but two qubits can hold four possibilities, 0, 0, 1, 10, 11, while three qubits hold 8. Each additional qubit doubles the possibilities, creating a landscape of exponential growth. This isn't a mechanical process. It's a natural unfolding, like the way a single seed can grow into a forest. Quantum computers use this property to solve problems that would take classical machines centuries to address. Problems involving complex molecules, intricate financial models, or the vast networks of the universe itself. But the magic isn't in the speed. It's in the way these possibilities gently interact, like the way ripples from a stone in a pond gradually merge into one smooth, unified wave. Rhetorical questions often help us understand the quiet power of superposition. What if your thoughts could exist in 1,000 places at once? What if the answers to life's greatest mysteries were already woven into a single, shimmering thread of possibility? In the quantum world, these questions find their answer not in distant stars, but in the gentle hum of reality itself. When a quantum computer solves a problem, it doesn't pick one path. It gently guides all the possibilities toward a single, clear answer, like the way moonlight finds its way through a window and illuminates a room without ever being lost. This is the quiet revolution of superposition. It transforms the impossible into the possible with a single, unified breath. The challenge of quantum computing, however, is not one of speed, but of delicacy. Quantum states are incredibly fragile, like the delicate balance of a spider's web in the wind. A single vibration from the outside world can cause a qubit to collapse from its superposition into a single state, just as a gentle breeze might disturb a still pond. This fragility is why quantum computers require such extreme environments, near absolute zero temperatures and perfect isolation, to protect the delicate dance of superposition. Yet even in this fragility lies beauty. The struggle to maintain superposition is a quiet dance between the quantum and the classical, a dance that reminds us that the most profound discoveries often arise from the most delicate balances. As Dr. John Preskill, a leading quantum theorist, reflected during a quiet moment in his laboratory, the real wonder isn't in the speed, but in the way quantum systems weave possibilities together. It's like watching a single drop of water become the ocean, slow, gentle, and utterly transformative. This perspective shifts our focus from the technical to the deeply human. Superposition isn't about brute force or speed, it's about the quiet art of connection. It reminds us that the universe operates not in isolated points, but in interconnected waves, a truth that resonates with the deepest parts of our being. What happens when we allow this superposition to guide us? Imagine a problem that seems impossible, like finding a specific grain of sand in an entire ocean. A classical computer would search one grain at a time, a slow, exhausting process. But a quantum computer, by harnessing superposition, would explore all grains simultaneously, not as separate paths, but as a single unified wave. The answer emerges not through trial and error, but through a gentle, natural alignment of all possibilities. This is the quiet power of quantum computing. It transforms the impossible into the possible with a single, unified breath. The next step in this journey isn't about building faster machines, but about understanding the language of possibility itself. Quantum computers don't replace classical systems. They extend our capabilities in ways we've only dreamed of. They help us see the world not as separate pieces, but as a single, interconnected whole. When you close your eyes tonight, imagine the quiet hum of superposition, how it exists in the way a single leaf moves in the wind, how it holds the potential for 1,000 stories in one gentle ripple. This is the true gift of quantum computing. It teaches us to listen to the language of possibility, a language that speaks not in numbers, but in the quiet whispers of the universe itself. Rhetorical questions often serve as bridges between the known and the unknown. What if the answers to your questions were already within you, waiting to be gently released? What if the universe's deepest secrets were not hidden, but woven into the fabric of superposition? In this quiet space, we find that the most profound discoveries come not from shouting, but from listening. The quantum world speaks in probabilities, not certainties. It reminds us that the path to understanding is not a straight line, but a gentle spiral, where each possibility gently leads to the next. As the ancient Greek philosopher Heraclitus once observed, you cannot step twice into the same river. This truth resonates deeply in the quantum world. Each quantum state is unique, fleeting, yet connected to all others in a quiet, unbroken thread. Superposition is not a temporary state, but a permanent feature of reality, a way of being that allows the universe to hold infinite possibilities within a single, unified wave. This is the quiet revolution that quantum computing reveals. The power to exist in multiple states at once is not a technological marvel, but a fundamental truth of existence. The beauty of superposition lies in its simplicity. It requires no complex machinery or overwhelming calculations. It is a natural state of being, as quiet and gentle as the breath of a sleeping child. When we understand this, we see that quantum computing isn't about building machines that outperform nature, but about learning to live in harmony with the universe's quiet language. It teaches us that the most profound questions are answered not by force, but by gentle alignment, by the quiet art of possibility. So as you rest tonight, let the quiet hum of superposition settle within you. Feel the gentle pulse of possibility stretching across the universe, a single thread holding infinite stories. This is the quiet gift of quantum computing. It reminds us that the universe is not a place of isolated points, but a vast, interconnected tapestry where every possibility gently weaves toward a single, unified truth. The next chapter of your journey won't be about speed or power, but about listening to the quiet language of possibility that already exists within you, waiting to be gently released. Let the gentle dance of superposition guide you toward the stillness that lies at the heart of all understanding.